Hey there. So, today we're going to dive into a really fundamental concept in electromagnetism, potential energy. Specifically, what happens when you take a charge and just plop it down into an electric field that's already there? How much energy gets stored in that system? And what does that energy actually depend on? Let's find out. All right, so here's our game plan. We're going to start with the simplest case you can imagine, just one lonely charge. Then we'll crank it up a notch and see what happens when we add a second one into the mix. From there, we'll check out a super important special case called an electric dipole. And finally, we'll wrap it all up with the key formulas you'll want to have in your back pocket. Okay, first things first, we've got to understand the foundational block for everything else we're going to talk about today. What happens with just a single solitary charge in an existing electric field? Before we get to the complex stuff, we have to nail this down. Now, here's a really important distinction we need to make right away. We only care about the work it takes to move our little charge, the one we're interested in, into the field. The energy it took to make that big external field in the first place, we're going to completely ignore it for now. It's kind of like placing a bowling ball on a hill. We only care about the ball's potential energy because of its spot on the hill, not the massive geological work it took to form the hill itself. And this all leads us to a formula that is just beautifully simple. The potential energy is just the charge, Q, multiplied by V. So what is this V? Well, V is the electric potential at that specific point in space. You can think of it like the electrical height of that location. You know how a higher physical height means more gravitational potential energy for a rock? Well, a higher electric potential V means more electrical potential energy for a positive charge. Simple as that. Now, when we're talking about the teeny tiny scale of atoms and particles, the joule is just way too big. It's like trying to measure an ant with a ruler marked in kilometers. So, physicists came up with a much handier unit called the electron volt, or EV. It's perfectly scaled for the subatomic world because it's literally defined as the energy an electron gets when it zips through a potential difference of 1 volt. And just look at the conversion. It really shows you how small this thing is. 1 electron volt is a mere 1.6 times 10 to the negative 19 joules. It's an unbelievably small packet of energy, but when you're dealing with what a single electron is doing, it's the perfect yardstick. Okay, so we've got a handle on a single charge. Let's build on that. Things get way more interesting and a little more complicated when we bring a second charge into the picture. It's not as simple as just calculating the energy for each one and adding them up. Nope. We have to be a bit more clever because now the charges don't just feel the external field, they feel each other. So we have to think about 3 separate jobs, 3 distinct bits of work. First, the work to bring charge Q1 in from way out at infinity. Second, the work to bring charge Q2 into that same field. But here's the kicker, the crucial third piece. As we're bringing in Q2, we're also fighting against the electric field created by Q1 itself. They're interacting. This 3-step process leads us straight to our total energy formula. And you can literally see the 3 parts right there. The first term, that's the energy of the first charge in the external field. The second term is the energy of the second charge in that same field. And that third term on the end, that's their own personal business, the mutual potential energy between the 2 charges. It depends on both charges and how far apart they are. Okay, to make this feel a little less abstract, let's plug in some real numbers using the example from our source material. We've got 2 charges, one's a positive 7 microcoulomb, and the other is a negative 2 microcoulomb. They're placed at specific points inside an external field that gets weaker the farther away you go, just like gravity. So, just like our formula told us to do, the plan is to calculate those 3 energy terms one by one. First, the energy of charge 1 in the external field. Then, the energy of charge 2. And finally, the energy from their own interaction. After that, we just add those 3 numbers up to get to grand total. And after all that number crunching, we get a total potential energy of negative 49.3 joules. Wait, what does that negative sign mean? Well, it tells us that energy is actually released when we assemble the system. It means the final arrangement is more stable, more comfortable, if you will, than having those charges infinitely far apart. All right, now for a really special and, honestly, an incredibly important setup of 2 charges, the electric dipole. This thing shows up everywhere in physics and chemistry, from how a water molecule behaves to how a radio antenna works. So what is a dipole? Fundamentally, it's dead simple. You take a positive charge and an equal negative charge, and you hold them a small, fixed distance apart. That's it. We can describe this whole setup with a single vector we call the dipole moment, p, which is just an arrow pointing from the negative charge to the positive charge. It basically captures the dipole's built-in electrical direction. This diagram is the key to understanding what happens next. Take a look. You see the uniform external field lines, E, all pointing to the right. And sitting in this field is our dipole, with its positive and negative charges. That vector P is the dipole moment we just talked about. And the most important variable here is that angle, theta. It's the angle between the dipole's orientation and the direction of the electric field. Now here's the really cool part. Because the field is uniform, it pulls on the positive charge and pushes on the negative charge with forces that are exactly equal and opposite, so they cancel out perfectly. The net force is 0, which means the dipole isn't going to get yanked across the room. But, and this is a big but, these two opposing forces create a twisting effect, a torque. It tries to rotate the dipole to get it to line up perfectly with the field, kind of like a compass needle. And this twisting leads to another beautifully simple result. The potential energy of the dipole doesn't depend on where it is, but entirely on how it's oriented. The energy is lowest, meaning it's most stable, when it's perfectly aligned with the field, and it's highest when it's pointed exactly against the field. Mathematically, we write this as the negative dot product of the dipole moment and the electric field. The dot product is just a handy mathematical tool that captures this dependence on the angle. Whew, okay, we have covered a lot of ground, from single charges all the way to the twisting dance of dipoles. So let's just hit pause, take a breath, and pull it all together. Think of this as your personal toolkit for potential energy. And here it is, everything in one neat package. For a single charge, energy is just its charge Q times the potential V. For two charges, you add up their individual energies in the field and then add their own mutual energy. And for an electric dipole, the energy is all about its orientation, given by that nice dot product, negative P dot E. And that leaves us with one final forward-looking question. We figured out how to define and calculate all this stored potential energy. But the real magic, the whole point of it all, happens when this potential energy gets converted into kinetic energy, when forces do work and make things move. That is the principle behind every electric motor, every battery, every single circuit. And that, my friends, is where the real action truly begins.